So Alan and I are now going to talk about water management in the Delaware River Basin. And we're going to approach this presentation by covering a few key themes or topic areas that relate to water management for drinking water, wastewater, and stormwater utilities. If you go to the next slide. And the first major theme we're going to talk about is the fact that climate change is water change. So next slide. What we mean by this is that as the atmosphere is warming, it is directly impacting the hydrologic cycle. And that's what this illustration is showing here, right? A cycle that I'm sure we're all very familiar with and includes processes like condensation, precipitation, evaporation, and transpiration. If you go to the next slide. And there are actually three main principles that help us understand how specifically climate change is affecting the water cycle. The first principle is that of atmospheric holding capacity, which is just a fancy way of saying that warmer air holds more moisture than cooler air. And if you're a PWDer, you have seen this sponge slide before. So we like to use the sponge analogy, which basically says that if the atmosphere is a sponge, the warmer it gets, the bigger the sponge gets. So it's able to retain more moisture before releasing it. And this leads to more intense precipitation events and can also lead to longer dry periods in between precipitation events. The second principle is fairly straightforward. It's that warm air increases evaporation and transpiration rates, which directly impacts the water cycle. And then the third principle is that temperature changes influence global circulation patterns in the atmosphere and ocean. And these circulation patterns also affect weather patterns like El Nino and La Nina, which in the past water resource managers have used to help make planning decisions, especially in the realm of drinking water supply planning. Next slide. So there is another water cycle that we need to talk about since we're talking about water management at water utilities, and that is sometimes referred to as the urban water cycle, which is shown here. This cycle is basically relevant at localized scales and in densely urbanized city centers like Philadelphia and New York. And if we start at the top of the cycle, we have a drinking water supply for utilities. That drinking water is treated and distributed to our customers who then use that drinking water. And then as utilities, we collect the wastewater from customers as well as stormwater from rainfall events and channel all of that wastewater and stormwater to our treatment facilities, which then discharge treated effluent into our receiving waters. And in some locations, receiving waters can directly impact drinking water supplies, especially when we're dealing with surface water supplies like rivers. And we know that climate change is impacting all of these different components of the urban water cycle. And if you click forward once, I'll go through a series of these impacts with some photos. So one impact is that as air temperatures are warming, they're also warming our water temperatures in our surface water supplies. And this can degrade water quality, leading to things like harmful algal blooms. This photo is of the Schuylkill River in Philadelphia, and this is showing growth of a harmless plant called duckweed, but we are concerned that we might start to see things like harmful algal blooms in the future. Next. Another impact we need to consider is drought. So if climate change is going to make drought more frequent and severe, like Alan mentioned earlier that it might, we need to be prepared for impacts to not just our water quantity, but also our water quality in the basin. Next slide, or image. Another major impact for us in the Northeast region is increasingly intense and frequent rainfall events. And this image is showing flooding in New York City during Tropical Storm Ida. These rainfall events overwhelm our drainage systems, which leads to things like localized flooding, basement backups, and more combined sewer overflows. And then, of course, in the context of this cycle, if we see more CSOs, we are affecting our receiving water quality, which again can impact our drinking water supply. So it's all connected. Next slide. And then the last impact I'll point out is sea level rise. We face a lot of risks related to sea level rise. One of those is inundation of some of our critical infrastructure in coastal communities in the Delaware River Basin. And PWD has been studying this risk extensively. This GIF is going through an animation showing 1 through 7 feet of sea level rise in the vicinity of our Southwest Water Pollution Control Plant, which is our most vulnerable treatment facility to sea level rise. So next slide. Alan and I also really wanted to point out that in the context of the urban one water cycle, New York City DEP and PWD services touch on all these different components of the cycle. So we're sometimes referred to as combined utilities or one water utilities. And PWD specifically provides drinking water to about 1.7 million customers by treating and delivering over 300 million gallons per day. And the source of our drinking water are surface water supplies, the Schuylkill and Delaware rivers specifically. We also collect and treat over 522 million gallons per day of wastewater. And we manage stormwater through a collection system that is 60% of a combined system, which means that the wastewater and stormwater flow into the same set of pipes in 60% of the city, and then the other 40% of the city is served by a separate sewer system. Next slide. I also just briefly wanted to point out in the context of Philadelphia that we are located at the very bottom of the Delaware River Basin, which is shown in green on this map. And the Schuylkill River watershed, a major tributary, is highlighted in yellow. So what this means is that we have jurisdiction over less than 2% of the land area that impacts our water supply. And for this reason, we highly prioritize partnership-based approaches to drinking water supply protection. And that's something I'll touch on a bit more later in the presentation. I'm going to now just briefly hand it to Alan to talk about New York City DEP's services.
Thanks, Julia. Next slide, please. So just very briefly before I hand it right back to Julia. So New York City DEP, as many of you likely already know, serves over 9 million customers, delivering over 1 billion gallons of water per day. So you can see from the last slide, we have the overlapping areas from the Catskill Delaware watershed, but a larger watershed that also includes the Croton system just north of the city. All of that makes its way to New York City, and we have a lot of common themes with Philadelphia in that we have a combined sewer system, partially combined, partially separate. We discharge wastewater or treat and discharge wastewater from 14 wastewater treatment plants in the city. And one key difference is that we're discharging to the essentially the Atlantic Ocean. So it's once through system, but we increasingly want to consider the whole water cycle and ways to maximize efficiency, conserve water, and so forth. And with that, I will pass it back to you, Julia.
Great, thanks, Alan. So if we go to the next slide, the next major theme or topic we want to review with you all is what we're calling the water utility context. Basically, we're trying to answer the question, what are some of the main factors we as water resource managers need to consider to ensure the provision of safe, reliable, and equitable services in a changing climate? If you go to the next slide, one of these major factors is regulatory compliance. And regulatory compliance is really the primary driver for water, wastewater, stormwater infrastructure investments. Utilities need to meet regulations and standards under the Safe Drinking Water Act and the Clean Water Act. And in the Delaware River Basin, through the Delaware River Basin Commission, or DRBC, we also have water quantity and quality standards that reflect the fact that the waters of the basin are a shared resource. And if you click ahead, within the context of regulatory compliance, we are dealing with many uncertainties as utilities, and a few examples are listed here. So we're currently grappling with evolving and often more stringent regulations, emerging contaminants, which are closely related to these evolving regulations on the drinking water side, especially uncertainties around politics, agency priorities, organizational structure, For example, do we have the staff and programs in place to carry forward the work that we will need to carry forward as the regulatory landscape evolves? And funding. This, of course, again, came up a lot in the pre-workshop survey that funding is a major challenge. All here today, climate change, right? One of the major uncertainties we're grappling with. So regulatory compliance is really the first major consideration. If you go to the next slide. Another big consideration is how we maintain high levels of service. And some challenges here for utilities include the fact that we have aging infrastructure systems. We're dealing with land use changes and development, especially for utilities located in urbanized areas. And we're dealing with changing environmental conditions due to climate change and other factors. And when utility managers plan and design resilient infrastructure systems, we often consider things like the useful service life of these systems, which in the utility context is usually on the order of several decades, if not more. We also consider the criticality of assets and systems, which is usually high because we provide critical services to the communities we serve. And the adaptive capacity of our assets and systems do vary. It depends on the solutions that we choose to plan, design, and implement. But something to highlight here is that because of climate change and all the other uncertainties we're facing, we need solutions as utilities that will increase our adaptive capacity. And both structural solutions like in systems and assets and non-structural solutions like policies need to be considered in this context. So I'm going to pass it off to Alan to keep going through some of the main considerations.
Thanks, Julia. Next slide, please. So one of the key considerations is water equity, and this is increasingly a focus for WUCA. We are partnering currently with the U.S. Water Alliance, who has been focused on this topic for quite some time now, to determine how we can better integrate water equity into our work. Within the definition provided by the U.S. Water Alliance, you will see that climate risks are specifically called out, and it is more than just the climate risks. So over the next few years, this is actually something that WUCA has determined, is really key to our strategic plan and to all of the work we do, is how to better integrate equity into our work. So please stay tuned. If any of you are attending the U.S. Water Alliance One Water Summit coming up next month, we will actually be hosting a learning lab, which we hope you can attend. And then moving forward next year, we will be developing a roadmap for incorporating climate and equity work. So next slide, please. So, we've discussed, or Julia has described, that we have a lot to balance. And one of the things that can be thrown off balance in this mix is affordability. So we have to be really careful about that. On one hand, the investments that we are making and need to make in the system have to be balanced with the need to keep rates low. On the other hand, investing in climate adaptation can reduce costs and help maintain affordability. Investing, as I think we've all heard and understand, investing now can save us and our ratepayers money later. We also have to ensure fiscal stability and demonstrating to our ratepayers and our credit rating agencies that we are proactively investing in preparedness and climate change, mitigating climate change risks is very important. We, over the last couple of decades, the funding that we had received from the federal government to invest in our systems has dwindled quite a bit, but we are eager to see that investment increasing over the last couple of years with the IRA and other federal funding. So again, really want to be able to strike this balance. And if you go to the next slide, just to summarize. So from a utility perspective, it's essential to reduce these risks and ensure that we continue to meet our evolving and more stringent regulatory requirements, maintaining high levels of service under changing conditions, providing equitable service delivery, maintaining affordability and financial stability. So for every dollar, we are spending in the system, we go back to this perspective of One Water and how do we maximize our investments so that they are covering as many bases as possible and robust in the face of climate change. Next slide, please. All right.
Okay, we continue the tag team. So we only have a couple minutes left. So I think we're going to go pretty quickly through some examples of adaptation and One Water management in practice at New York City DEP and PWD. If you go to the next slide. Something we wanted to highlight before going into specific examples is the range of scales that we need to as water resource managers, which is pretty amazing when you think about it. So we're not only working at basin scales, especially in the context of drinking water supply protection and management, we're also working all the way down to project scales. And I have a photo here of a green stormwater infrastructure in Philly to make that point. So huge range of spatial scales that we're working across. And then if you click one forward, across a really wide range of temporal scales with the data and models that we work with. So depending on the application, we can be working with annual or seasonal data, all the way down to sub-hourly or even 15-minute data. And that's particularly used when we're trying to model and understand the performance of our urban drainage systems. If you click forward. So across all these scales, we need to be able to effectively apply climate change information and science. And this is a bit of a complicated matter because the projections we're using come from global climate models or GCMs. And as the name implies, these models are simulating processes and developing output at lower resolution, so on really global scales, and much lower resolutions than what we need to perform a lot of the risk assessments and analyses that we do as utilities. So this is something that I think we might get into discussion a bit more throughout the workshop, and I think Dan and Abby might touch on this as well, but definitely something to keep in the back of our heads as we talk about the science and its applications. Next slide. So the first example I wanted to quickly are the data, the models, and the tools that we employ to understand and characterize our systems. I'm not going to run through this whole list of models, but you can see that we have models to help us understand things about our drinking water system, our wastewater system, and our stormwater system. And with these models, we're really trying to do things like plan for existing and future regulations, and investment needs, and understand changes that might impact our quality or performance levels as a utility. And so you can see here we have examples like hydrologic and hydraulic or H&H models, hydrodynamic models, reservoir optimization models, hydraulic models through our treatment facilities, and also a series of warning system tools. And if you click forward, if we want to apply climate information to all of these models and tools, we need actionable science, which is something that WUCA has done a lot of work around. And examples of actionable science that PWD's climate change adaptation program has produced include high-resolution precipitation projections, localized sea level rise and storm tide projections, as well as air and water temperature projections. So this has been a big focus of our program's work over the years to help generate actionable science. Next slide. Another example I'd like to highlight that goes back to the point I made earlier that Philadelphia is at the bottom of the Delaware River Basin watershed is the fact that partnerships are very important to us. And one of our most successful examples of watershed scale coordination is the Schuylkill Action Network, or SAN. SAN was established in 2003 and was started with an EPA grant in the amount of $1.15 million. Since then, millions have been leveraged for on-the-ground implementation of best management practices that have helped to improve our water quality in the Schuylkill River watershed and deal with sources of pollution like abandoned mine drainage, stormwater and agricultural runoff, and point source discharges. Next slide. Now going back in scale, more back down to the project scale, our climate change adaptation program has developed a set of climate resilient planning and design guidance that provides information to our staff and consultants on what projections they can use in their work, specifically in their infrastructure planning and design work. And this is really our fundamental reference document for mainstreaming the use of climate change information at PWD. And a big shout out to my team members, Sega, Ashley, and Allison, who are currently working through an update to this guidance document, because as we all know, the science is ever evolving. So it is a living document. And in January 2022, we were able to adopt a department-wide policy that requires the use of this guidance document in all of our infrastructure planning and design processes. So that was a really big step forward for us in terms of effectively mainstreaming the use of climate information at PWD. Next slide. And the last example I'll provide for PWD is our Green City Clean Waters program. And this is an example of an adaptive management strategy, specifically in this case with using green stormwater infrastructure, or GSI systems. Green City Clean Waters is a multi-billion-dollar 25-year program that we have in place to meet our combined sewer overflow regulations. And we have implemented projects throughout the city. You can see by the dots on this map that we have put in place many, many projects on both public and private land. And we consider this to be an adaptive approach for several reasons, namely that these GSI systems are decentralized in nature, and we can modify their plans and designs over time as the climate changes. So with that, I'm going to hand it back to Alan to go through some examples from New York City's side of things.
All right, a couple more slides, and I'm going to keep it really quick because I know we're running a little bit over here. So if you go one more, most of you may already be familiar with the New York City Watershed Protection Program and the filtration avoidance determination. And this is really, one of our regional examples of green infrastructure, which we're now applying in city to, the green infrastructure program that Julia mentioned, which is helping us with other issues like combined sewer overflow. In the watershed, this continues to be a multiple layers of defense approach, where we're investing in many different programs instead of a large centralized filtration facility. Next slide, please. We still do need to make improvements and prepare for gray infrastructure investments. This is an example of a connection between within the system that allows us to throttle supply when there's high turbidity. Next slide, please. And we continue to make improvements in monitoring and data, how we use data, decision support, specifically in this example, the operations support tool, which we can run both operationally as well as in simulation mode, where we can show what potentially, how we can respond operationally to changes in the future. Next slide. We are also applying design guidelines in New York City. All of our wastewater facilities have some risk from sea level rise and coastal flooding. And one more slide. And we are also looking increasingly at how do we let water in. So there's the first line of defense, which is infiltration through green stormwater infrastructure. But once all of our sewers and are full and the ground is saturated, can we actually create areas that can flood safely. And this is what we're calling our cloudburst approach. Next slide. So finally, just to bring it back full circle, we can't wait for perfect information necessarily. So how can we make decisions with the information we have available? How can we better work with climate scientists to co-create actionable science at the local and basin scales? And how do we develop flexible and adaptable processes and solutions? All right, thank you.